Okay, so for question number 5 here, if I use an average force of 40 newtons, okay, and I compress a spring 0.1 meters, okay, and then this ball is placed on the spring, can I calculate the amount of work I did? Okay, I know the force, I know the distance, agreed? So what's 40 times 0.1? 4 joules. I did 4 joules worth of work. Okay, how much energy is in this spring system, spring and ball system? 4 joules. That's all any part of this thing can ever have, because that's all the energy I put into it by doing work. Okay, so what happens to the work done on the spring? It becomes what? What kind of energy is stored in a spring? Yeah, elastic potential energy. So I compress the spring. The spring wants to go back to its normal shape, but I've done work. Okay, so now there's potential energy stored in it. Okay, if the spring is released, what happens to the energy of the spring? So I've got this spring, it's sitting on a desk, I've compressed it down and I put a ball on top of it. If I let it go, what will the spring do? Yeah, it'll release. Okay, so I release the spring. What does the spring do to the ball? What's that called? No, transfer of energy is called 4-letter word, starts with W. Work. Yeah, okay. The spring will do work on the ball. It will transfer energy, mechanical energy, to the ball. Okay? So calculate the energy the ball has the instant it leaves the spring. Nothing to calculate. How much energy can it possibly have? 4 joules. That's all the energy I put into the system. Okay? Again, this is that idea of how work energy theorem ties into the law of conservation of energy. The only energy in the system came from my 4 joules worth of work. Nothing in that system can have more than 4 joules worth of energy. Okay? So when I release the spring and it shoots the ball up in the air, the ball can have 4 joules worth of energy. Okay? What will the speed of the ball be when it leaves the spring? Well, when it leaves the spring, it will have kinetic energy. Everybody okay with that? How much kinetic energy will it have? Four joules. Okay, so that equals 1/2 mv squared. I know what m is. They told me it's 0.01 kilograms. Okay, and I know the energy, 4 joules. All right, so all I have to do is go V equals the square root of EK over 1/2 of m, and I'll have my 28.3 meters per second. Okay, it's just work energy theorem stuff. It's the stuff we did before, okay, but it's also related to the law of conservation of energy. Okay, as long as you understand that once you do that 4 joules worth of work, that system has 4 joules worth of energy, and it can use it to do whatever it wants. In this case, it's launch a ball. Okay. If the ball is fired straight up off the spring, how much gravitational potential energy will it gain? 4 joules. That's all it can ever have. 4 joules. Okay, and we can calculate its maximum height by saying 4 joules equals m times g times h, and solve for h. Okay, and that's all that was done there. Okay, that making sense, everybody? Okay, so that's one of those concepts we have to understand. Energy can't be created, and it can't be destroyed. So once I put 4 joules worth of energy in that system, that's all it can have. Okay? It can't have more, it can't have less, because it can't create energy and it can't destroy it. Okay? Everybody all right with that concept? All right. Okay, I want you to copy down this terrible drawing of a roller coaster. So in this problem, we have a roller coaster with a mass of 1,600 kilograms. It is at the top of a 50-meter high hill. And it is moving at 5 meters per second. It then goes down the hill, and a little while later is on top of an 8-meter high hill. I would like you to calculate how fast it is going on top of that 8-meter high hill. This is very similar to the one we did at the end of the day yesterday. We just calculated the final height instead of the final speed, right? So it starts out like this. The mechanical energy initially, which is here, is equal to the mechanical energy there. Okay? See how much you remember from yesterday. I'll give you a few minutes on that, and then we'll walk through that one together. You can. All right, so we're going to go through this kind of concept by concept, piece by piece. Okay? This is a conservation of mechanical energy problem. Because at no point when I was describing it did I talk about work or force or anything like that. So that means the mechanical energy here at the beginning is equal to the mechanical energy here at the end. How do we calculate mechanical energy? Yes?
You add the kinetic and potential.
Right. Okay. So that means initially, okay, I take the initial potential, I add the initial kinetic, and that's going to equal the same thing on this side, but final. Okay. So, is that okay? Have I said anything different? Okay, I'm still saying initial mechanical equals final mechanical, yes? Okay. Are any of those forms of energy in this situation 0? No. Okay? At the beginning, we're 50 meters off the ground, so we have initial potential. We're moving at 5 meters per second, so we have initial kinetic. At the end, we're told we're 8 meters off the ground, so we have potential. And if we're only 8 meters off the ground at the end, we're definitely moving. Okay, so we definitely have kinetic energy. They wouldn't have you solve for VF if it was 0. Okay, so I can't cancel any of those off. They all have a non-zero value. Which one of those terms is VF part of?
Final kinetic.
Final kinetic. So I need to get final kinetic energy by itself before I plug in all the variables, because then it starts to get confusing. Okay, so right now, if I want to get final kinetic by itself, what do I do with final potential? Subtract it over to the other side. Okay, so that's going to give me initial potential plus initial kinetic minus final potential equals final kinetic energy. Okay, everybody okay with what I have written there? Right, essentially what I'm saying is mechanical minus potential equals kinetic. Okay? All right, now I want to put in all my formulas. So I've got initial potential will be m times g times h initial. Initial kinetic will be 1/2 mv initial squared. Final potential will be m times g times h final. And final kinetic will be 1/2 mv final squared. Okay. At this point, you have a choice. What can I do with m if I want to? I can get rid of them. Okay? It's in every term. Okay? I'm not solving for any energy types where mass would be important. I'm just solving for speed. So I can cancel off the mass. If you're not if you're not comfortable with that, you can leave it in there. I did give you the mass after all. It's 1,600 kilograms. Okay? So mass is going to cancel off. All right. I just want VF by itself. So how do I move the 1/2? I divide by it. Okay, that leaves me with VF squared. I just want VF. So what do I have to do to that whole thing? Square root it. Okay. All right, that is the most involved algebra you will ever have to do in this course.
Is there going to be something like that on the test?
Absolutely. I put a roller coaster question on the test. That's why we're going over a roller coaster question. Okay. So now that I've got that, now I can plug in my numbers. Okay, so I can say 9.81 times 50, so there's my initial potential, plus 1/2 times 5 squared, my initial kinetic, minus 9.81 times 8, my final potential, divided by 1/2, square rooted, will give me VF. Okay, so 9.81 times 50 plus 0.5 times 5 squared minus 9.81 times 8 divided by 1/2 square rooted. 29.14 meters per second. I did notice that several of you had that number written on your sheet when I walked around, so good job. That's as hard as they get. Okay, and the one we did yesterday at the end of class, where we find final height, also, that's as hard as they get. Okay, it involves the most manipulation, okay, and the most understanding of the concept. So 29.1 meters per second. Okay, does that answer make sense within the context of the question? It absolutely does. Okay, if it was only going 5 meters per second way up here, it should definitely be going faster down there. Okay. All right, questions on how that one worked? Okay. Has the method been the same for all of these questions that we've done? Absolutely. That's the thing about grade 10 physics, at least. Okay, is that it's very cookbook. Okay, it's like, do this step, then do this, then add the flour, then, like, it's very much, okay, as long as I know the pattern, I can do the question. All right. This is just like the one we did at the end of the day yesterday. It's literally, it's a toboggan going down the hill. So it's just like the one we did yesterday, just different numbers. So if you're needing a little bit of help as you're going along, you can ask me, or you can look at the one we did at the end of the day yesterday. But give this one a try. Okay? Give you a few minutes and we'll walk through it. All right, I'm not going to go through the whole thing. I'm just going to kind of set it up a little bit here. So this is the situation we're dealing with. We got our toboggan, okay? And at one point it's 30 meters above the bottom, okay? And it's moving at 14 meters per second. Okay, so this is kind of our givens for the question, right? What did they not give me in this question? Mass. If you don't like that, pick whatever you like. Won't make any difference. Okay? You can make it 200 million kilograms, or you can make it 0.2 kilograms. It won't make any difference. Okay? And then a little while later, we've got the final height, which is what we're looking for, and the final speed being 23 meters per second. Okay. Right. Give you a couple more minutes to finish that up. Okay, so for this one here, okay, again, we know that because work is not mentioned, we're not given force, okay, that this is not a work energy theorem problem, that this is a law of conservation of energy problem. So we started out, EI equals EF. Our initial mechanical energy and our final mechanical energy are the same. Okay, that means initial potential plus initial kinetic equals final potential plus final kinetic. Okay, are any of those zero in this problem? No, they all have a value. Okay, what I'm looking for is final height. Which term is that part of? EPF. Okay, so I've got to get EPF by itself, so what do I do with EKF? Subtract it over to the other side. All right, so EP initial plus EK initial minus EK final equals EP final. All right, now I can plug in my formulas and expand this out. M times G times H initial plus 1/2 MV initial squared minus 1/2 MV final squared equals M times G times H final. All right, I wasn't given mass in this question, because I don't need it. What do I have to do to get HF by itself? Yeah, just divide by G. Alright, now I can plug in my numbers. So 9.81 times 30 plus 1/2 times 14 squared minus 1/2 times 23 squared divided by 9.81 will give me my final height. 30 is 0.5 times 14 squared minus 0.5 times 23 squared divided by 9. All right, so they've gone a little more than halfway down the hill. Okay, they're now only 13 meters above the bottom of the hill. Okay, how did that one go? Okay, are we feeling a little more comfortable with those than we are with the work energy theorem ones? Okay. If you're feeling better about these, let me tell you something that'll make you feel better. I hope. These are harder than work energy theorem. Okay? You have to deal with potential, you have to deal with kinetic, you have to deal with initial and final. Work energy theorem, it's either potential or kinetic. It's never both. Okay? Only one of them is changing. Yes, you got an initial and a final, but it's only one energy type. Okay? So they're actually less involved than these are. On a test, this could be between 6 and 8 marks. A work energy theorem question, 5 marks, maybe 6. Okay? There's less to do in a work energy theorem question than there is in one of these. Okay. Okay. This is yeah. It was all a stunt though. It was like for Hollywood. Nobody was in the car. Okay? Give this one a try. We'll call it a day after this one. So just in case you're done, because I don't think everybody will be before class ends, okay? In case we don't get a chance to go over it, if you want to check your answer, I think it's 111 meters. Okay, how many people are done? Oh, okay, all right. You know what, we might have time to go through it. I'll give you one more minute here and then we'll quickly go through it. Okay, so there's our cliff, okay? That's a car. It's initially going 25 meters per second, okay? And once it drives off the cliff, down to the ground, okay? Where it's going 53 meters per second. So this is our VF, okay? This is our VI. We're looking for the initial height. What's the final height?
0.
0. Makes it a little bit easier. Okay, so we're going to have, and I'm just going to abbreviate this so we actually get it done, m times g times h initial, okay, plus 1/2 mv initial squared equals 1/2 mvf squared. Okay, we only have kinetic energy at the end, so when we manipulate this, we'll be left with this. The initial height will be 1/2 vf squared minus 1/2 vi squared divided by g. Okay, because the m's are going to cancel, right? And that's what we'll be left with. So we will have 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. And when you do that, you should get 111 meters. Question?
I did something different, but that was
Look at your final formula. Then you should have got a negative number. Yeah. Yeah, you got to go final minus initial if you get a negative number. But yeah. Okay, because you're saying the car jumped out of the hole. Right? Your initial height would have been negative 111 meters. So somehow the car went, and came out of the hole.